Okay, so we're going to take the chain rule, and we all know what chain rule is, right? We pretty much know what chain rule is. It's the derivative of a derivative with stuff inside. So I want to show you guys the way they're writing it. And this is another notation that is seen a lot, actually. And it's the f of g notation with this little o. Come on, let's go. F of g notation with a little o. So you see it as g-o-f. Okay, g-o-f. This is exactly the same as g on the outside with f of 2 on the inside. So please take note of this. Whenever you see this g-o-f, that's really this composite function where you have the f on the inside and g on the outside. Whichever letter is first, that's the letter on the outside. Just to reverse this around, if I write f o g of 2, okay, this would have been f on the outside and g on the inside. Okay, big difference is a letter first is a letter on the outside. So it's just a fancy way of writing this composite function instead of writing all these parentheses, essentially. I mean, really, you have all the same terminology here, but I think it's cleaner for them to write that derivative. Okay, so what this is really asking for, it's the derivative of this whole problem. Okay, so when we normally take the derivative of this problem, we say g prime, leave the inside alone, right, times the derivative of the outside, derivative of the inside, f prime at 2. And then the idea is you plug in 2. So for these problems, we're going to set it up in this manner. But we're going to use a chart that gives us all the values we need. So let's go ahead and set this up again. If we're taking f prime of g, we're going to look at this statement here. So g prime of blank times f prime. So once you rewrite the derivative as a chain rule, go ahead and look up here for all the numbers we need. What is f prime at 2? Let's look at this one first. F prime at 2, f prime at 2 is -3. F at 2, f at 2 is 6. Now that we have 6, what is g prime at 6? G prime at 6 is 7. So it's almost like a little puzzle where we have to figure out what the function is before we can plug it in to look at the table. Okay, let me do this one more time. If I see g of f prime at 2, the derivative is g prime of f at 2 times f prime at 2. Okay? Now we look at the table for these numbers. What's that number? What's that number? F prime at 2, we said was -3. G, we can't find what g prime is till we plug in what f of 2 is. F of 2 is 6. Now we can go back and look what f prime at 6 is. That's 7 times -3. Gives us...
This is chain rule, right?
Yes, because they asked us to find the derivative, and this is a composite function with g as a little baby inside. So it looks a little messy. We're going to do this a couple more times. And when kids usually see this on a test, they're like, what the crap? Because this gives you no hint about any of this stuff here. It gives you no hints. But the idea is that this is a composite function, and I can take a derivative of this composite function, which leads us to chain rule. Same thing. Okay, we're going to do a couple more of these problems, and then you'll get a lot faster at it. Some people try to do this in their head once they're pretty good at it, but I think it takes a little bit to get there. Okay, so we said the answer was -21, I think. Oh no. Oh yay. Olay. Okay, so if you guys want to try this, go ahead and try this yourself. See if you can figure out the pattern. I'm going to go ahead and write my steps out. So this is really f on the outside and g on the inside. We're taking the derivative. So this is the huge notation about what they're trying to simplify. Take the derivative of f on the outside, g on the inside, chain rule. So remember for chain rule, don't plug in any values till you're done with the derivative. So let's take the derivative. That's f prime, leave g alone, times g prime of -6. That's legit chain rule. Derivative of the outside, leave the inside alone, and then times the derivative of the inside, chain rule. Okay, so I know I can find out what g prime of -6 is. G prime -6 is 3. G of -6 is 4. Okay, that's my first step. Now, let's go and find the prime of that. F prime of 4 is 4. 12. Okay, with a raise of hands, how many of you guys got this by yourself? Just wondering. Good. All right. Neato. This will be super fast for you guys. Or you can just click yes on the participants. Okay. All right. I'm going to do this 2 more times and to make sure we're kind of into the pattern. Thank you for responding, guys. And then let's go ahead and do this again. We said 12. I don't know. I forgot. Oh, yeah. Wow. Old man memory. Okay. Okay. I'm going to give you guys a moment to try writing this down. Take the derivative and see if you guys can give me a final answer, given the charts here. One cool thing about this is that there's no real number crunching on my side. It told me what the derivative is. Jacob, that was fast. You probably saw the 0.
Yeah, you didn't have to go any further.
You didn't. You're right. Just practicing it. Cool. How many feel that you're kind of getting a little better at this? Right. Good. And really, as fast as you can do it is super important because the AP exam, just like the SATs, if you can save a couple seconds here, you can donate it to a poor problem there. Okay.
Mr. Go, I have a question.
Yes, of course.
I know it's the chain rule and it's just a pattern and we follow it, but then how did they come up with the chain rule?
Okay.
I'm just wondering, where did it come from?
Where it came from.
Like
okay,
how the derivative
of
f of g of -4 translates to that.
Yeah, okay, so we did that way back when. Let's see if I can do it without messing up. Okay, so you agree with me, a function f of g of x, okay? This is the idea of a chain rule, right? Okay, so I'm going to change this up. I'm going to write this a little differently just to make it look a little different. And we haven't done this. It's called implicit differentiation, but let's take it as this. So when I take the derivative of this problem, the problem here, look at that. That is not the right variable. I should have an x. If this was a traditional problem written this way, the value x is there. The example is the derivative of f of x squared plus 2x. Okay, that is the same variable. So when you take the derivative here, this is really, if I take all the steps in the whole wide world, okay, I skipped a step there. But are you okay with me breaking it up?
Yeah.
2 is a constant, goes in front.
Mhm.
Now, what happens here? Isn't dx over dx just 1? Right, essentially?
Yeah, because it's a part.
The power rule here brings down the 2, and then we write x dx over dx. Oops, sorry. If we do the chain rule here, essentially, those cancel out also. And we're left with 2x plus 2. Fast way versus long way. Cool? Now I'm going to do the same exact idea here, except plug in the letter g. If I write f of g for the same function is equal to g squared plus 2g. Okay with that?
Yeah.
Okay, so if I try to take the derivative here, we end up with our power rule, and then we write now the problem is that what is this saying? Once you're done with this guy, go take the derivative of g, whatever g could be. And this is essentially where the chain rule comes from, is that after I do my power rule, you had to take the derivative of that variable. In this case, this was just 1, easy. But if it's not just the same exact variable, you have to go back and take the derivative of that g now. Now, if I plug in a problem, say f of x is f of sine instead, okay, because x became sine. So power rule 2 sine x. Now, then we take the derivative of sine. Oops. Oh, derivative of sine is, okay. So this is the derivative of sine. What's the derivative of sine? Cosine. So this is kind of like the idea of, in a traditional x problem, it cancels out because dx over dx is 1.
So when there are two variables, we need to develop.
You need to take the derivative of that second variable, whatever that is, if it's possible even. And in this case, g, we couldn't, so we just leave it as dg over dx till you tell me what g is. If g is sine, we could take a derivative of sine.
Yeah.
That is going to be cosine.
I get it. Thank you.
This is kind of like the idea of chain rule. We actually do chain rule way back here. But dx over dx is just 1.
Mm-hmm.
So everything actually has a chain rule. Even if I say this, d over dx of sine of x, this is cosine x, then dx over dx, chain rule. But that just becomes 1.
Can you go up a little bit, please?
Yep.
To copy the last.
It's just using examples that we know. But we can also just do this using functions, like what we did right at the beginning. Okay, Bobby, you have a question? Bobby? I can't hear you. Microphone's off.
What the? Huh?
Hey, Bobby. Do you have a question?
What is it to?
All right, let's go back. The question is, are there any good practice books for reviews? You can always do the Prentice Hall books, all those review ones. They're all like $10 on Amazon. But iExcel, I think, is a great place for you to just practice these problems over and over and over again. Once you get to 100, go back and do it again if you need the review. So I think IXL is a good resource. Okay, let's do one more of these problems, and then we'll move on. Okay, so this one's a little tricky because it's itself. Let's see if you guys can figure this out. I'm gonna give you guys a moment, and I will catch up to you guys. Don't make this too difficult. Okay, F prime. This is another zero
It's
problem.
the same numbers as the last problem, just without the G.
Gosh. And then if I wanted to write it, F prime of this was 9. It's the same numbers. Okay, well done. Well, hopefully you guys are seeing the pattern. And one cool thing is that the chart does all the work for me. Okay, the chart does all the work for me. Let's give you guys just one more. Hopefully the next one will be a little different.
I like the ones with zeros in them.
You know what? I think everyone does. Everyone does. I definitely do. Okay, here's another one, okay? Okay, see a couple of different answers. Okay, again, this is like a puzzle. Take your time. This is going to be d over dx of g prime. Whoops, not g prime, just g. G of f of -3. And then this is going to be g prime, derivative of the outside, leave the inside alone. Just leave me alone, times the derivative of the inside. Okay, we know what this is, -5. G prime of f at -3 is -1. And now what's the f prime of -1? That's going to be 8. And we end up with -40. Cool. Okay. Hopefully you guys are kind of getting used to the pattern. I write it out. It's easier in my brain, okay? But you could actually do these in your head. Okay, so here's our next problem that we're gonna work on. Now, today the hard part of this lesson is what we call derivative of inverse functions. The derivative of inverse functions. Okay, so first we're going to describe what an inverse function is. So if you guys remember inverse functions, they're denoted by this -1 exponent idea. And this is the idea of inverse. And essentially they are undue functions, okay? Or they're opposite functions, or they cancel out. It's cancel culture. This is the definition of cancel culture. It's going to undo, right? So the simple examples without getting into it it's that if I have x squared, okay, to cancel out x squared, I take the square root. And they essentially cancel the operation out. The operation of times 2 would be divide by 2, essentially canceling out the 2 out. We've done this in trigonometry. Sine inverse cancels out sine, giving us this theta. So pretty much in algebra 1 through algebra 2 in geometry, you worked on an operation and you learned how to undo that operation. E to the x was natural log. Log base 5 of 5 to the x was x. Let me do this one for you. Logs bring down the exponents, bring down the gods, and log base 5 of 5. What exponent of 5 gives you 5? That's 1. Just as a reminder for logs. Okay, so we learned a lot of opposite operations here. Does everything have an opposite operation? No, not everything has inverse, right? You can't always go back. Interesting thing about computer science and password protection, you have to have an inverse. If you want to code a password, you need to be able to decode it. That's inverse. They use prime numbers for that. Okay, so how do we create inverse problems? So if I give you a problem, let's say y is equal to x squared. We had a couple of steps to make this an inverse. First, we change, okay, depends how you write it. If I write f of x, first step would be changing it to y. That would really be the first step if you got f of x. Next step is you swap x's for y's and y's for x's. So this becomes x equals to y squared. So this is an algebra 2, algebra 1 activity. After we swap it, we then solve for y. So this becomes square root of x equals to y. Okay, and then afterwards don't forget the plus and minus, right? Whenever you take a square root, you have to include the plus and minus. And then one more step, step 3, is you change y to become f inverse. So here we go, of x. So square root of x is equal to f inverse of x. Now let's see if this works. So the idea is if I plug in a number into the function, the inverse undoes my messiness. So let's try f of 5 here, right? F of 5 is 5 squared is 25. Now, if I want to undo it, f inverse of 25 would be this function here, right? That function here, 25, gives me back 5. What we start off with is what we end with. That's what an inverse function does. Okay. Now, today, what we're going to do is take the derivative of inverse functions. We essentially are going to take the derivative of an inverse function. So this is a part that's a little bit confusing because we're going to go back and forth. But okay, so the rule is people would define it a couple of different ways. Let's define it this way for starts. It's 1 over f prime of f inverse, f inverse of x. And this, I feel like it's really confusing until you kind of get an idea what you're talking about. Okay? This is super confusing, right? So the derivative of my inverse is really the derivative of my original function. The derivative of the inverse function is really 1 over the derivative of my original function, but with a small caveat here. It's not x, it's the inverse value. Okay, so this essentially is kind of like your y value. Okay, so I want to include something real quick here. In this function here, if I plug in 5, we get 25 as a result. Okay, if I plug in f, I get f of x. Oops, sorry, other way around. X is 5, f of x is 25. But the inverse, if I plug in x is 25, I get 5. X is 25, f inverse is 5. Now, I'm going to write this a little differently. I'm going to change my little color. If this is x and y, this is y and x. Isn't that essentially what it is? Okay, let me say this again. If this is x and y, the inverse essentially is flipping my values. See, wasn't this my y and my x? Okay, so keep that in mind because that's going to be important to us. Okay, so here is my problem. If I'm telling you that remember, so another way of looking at derivative is, we said it was slope, right? It's the rate of change. It's how much something changes. So let's talk about the slopes that we talked about before. If I give you the graph x squared, the parabola looks like this, x squared. But the inverse graph, f prime of x, looks like square root of x. Draw this in red. Something like that. Okay, essentially that's what it looks like. So I'm going to help you guys out. I'm going to draw this separately over here. Draw that like that. Okay. Can you guys tell me what is the slope? What is f prime at 2? Please tell me what f prime at 2 is. Also tell me what is f at 2. Okay. Tell me what f prime at 2 is, and then tell me what f of 2 is. So f of 2 is 4, and the derivative, the slope at 2, the derivative of x squared is, we said, let's see, f prime of x is 2x. If I plug in 2, that becomes 4. Okay, where f is x squared. Okay. What did we say was inverse? Inverse was square root of x. So on this other right side, I want you to plug in these values. What is f prime of 4? And what is f of not f prime, f inverse of 4? Okay, what's the f inverse of 4? And what is the derivative of f inverse at 4? So just filling out a small table for us. Okay, what is f inverse of 4? Where does that take you back? 1, 2, 3, 4. Okay, and we can, oh, whoops, that's inverse here. Sorry here. Hey guys, sorry about that. That's inverse, okay? That wasn't prime, that was inverse. Okay, so in this problem, this would be the square root of 4, which is 2. And would you agree with me 2 becomes 4. So the inverse, 4 becomes 2. Brings you backwards. That's what inverse function does. So what is the derivative of the inverse function? Now go ahead and take the derivative of this guy. So what is the derivative of f inverse of x? Okay, so what's the derivative of the square root of x? And how fast can you do that problem? Hopefully pretty quickly. 1 over 2 square root of x. Oops, wrote it in the wrong spot. 1 over 2 square root of x. Okay, all the same thing. Okay, 1 over 2 square root of x. And if I want to plug in 4, plug in 4, plug in 4. 1 over 2 square root of 4, which is 1 over 4. Okay, we're going to do one more problem. Okay, we're going to do one more problem. This might not have answered anything yet. Shoot, I'm running out of time. Okay, so this might not answer anything yet, but we'll do this one more time. Okay, one more time. What is, so let's do our f of x now is x cubed, okay? X cubed. And the graph of x cubed looks like this crazy guy doing the YMCA. And tell me what is the derivative of f of x, and then tell me what is a couple of things. What is the value at 2? And also tell me what is the function at 2. Fill those out for me. I'm going to tell you the inverse. I'll do this real quick. So f inverse of x is equal to the cube root of x. So I want to find out what is first. What is, so the number I want to plug in is f inverse of 8. And then tell me what is the derivative f inverse of 8 d over dx. Okay. On the side, tell me what is the derivative function of f inverse of x first, to make it a little easier for you. Okay, all right. The derivative of x cubed is 3x squared. Pretty easy, right? Okay. Well, that's a lot more easier than taking the derivative of the inverse function. Shoot, this is the derivative of the cube root, rewriting that as x to the 1/3 power. The derivative is 1 over 3, x to the negative 2 over 3, subtracting 1, which we can rewrite this as 1 over 3, the squared of the cubed. Okay, you guys all hanging in there a little bit? So
All these problems escalate very quickly and it gets very confusing.
they get ugly fast. Yeah. So there's a reason for that. Because who wants to do the inverse derivative? Who wants to do the inverse derivative? Who wants to first find the inverse and then from the inverse take this derivative of something that could be potentially ugly? Because most of our inverse problems are ugly. It's like cooking is easy, but cleaning is a nightmare. Okay? All right. So let's go and finish this. The f prime at 2, plugging in 2. 2 squared is 4. 4 times 3 is 12. Okay? So at x is 1, 2. The slope is pretty darn steep already. Okay, the slope is 12 over 1. Over here, our point, if I plug in 2, is 8. Okay, so that's like 8, and that's 2. So everyone okay that the slope is 12? to graph this function here, the cube root of x, here's what you do. What's the cube root of 0? 0. What's the next cube root you know? What's the next easiest cube root that you know? The cube root of what number?
1.
1, good, is 1, right? What's the next cube root that you know?
2. It's 8.
Nope, cube root of 2 is like some crazy decimal. Thanks for trying though. Do you have another one?
I meant 8.
8, because we did it over here. So if I go 8 spaces out over here, this is what the graph looks like. It turns out this graph looks like that. Okay, it's like a tilted version. Okay. All right. So since this is so steep, the slope is pretty flat, isn't it? So I want us to plug in 8, because this is 8, right? So plug in 8 here. So I'm going to write this a little bigger so you guys can all see. 1 over 3, the cube root of 8 squared. So when you do squares and cubes, it doesn't matter the order. So what's the cube root of 8 first? What's the cube root of 8? That's going to be 2. 2 squared is 4. 4 times 3 is 12. So the slope here is 12. The slope here is 1 over 12. Do you guys see a similarity? A little bit? Let's go back up here. Our last problem, our easy one. What was our slope for our original problem at 2? At 2, 4, the slope was 4, right? What was the slope of its inverse? At 4, 2, it was 1 over 4. The thing about this inverse rule, let's go back and look at the rule now, is that the derivative of the inverse, it's actually the same exact value as the derivative of the original equation, but plug in your y value back in. Well, this is your y and this is your x. So if we look at this as 8, let's say this as, we call this x, right? But remember over here, this is the confusing part. Remember, in the world of inverses, x is really y. In the world of inverses, x is really y. So here is what I'm going to show you. Here's a pattern. Let's do the first one. The derivative of f inverse at 4. Okay, here's the point. In my regular world, if I plug in 2, I get 4. This is f. F inverse, if I plug in 4, I get 2. Is equal to 1 over the derivative of the regular derivative, but plug in, plug in 2. So that's an x. Plug in 2. Because what is the inverse of 4? Inverse of 4, the answer is 2. So the derivative of this guy here, it's actually just 1 over your easy derivative. Let me do this one more time. Say it one more time. The derivative of your inverse, okay, they're going to give you an x value, right? But that x value is really your x value, no, is really your, is really a y value. This is really the y value in the real world. See, that's really our 4 over here. So we plug in our 2 to find the derivative in the real world. If I'm looking for the derivative at 4, I'm really looking for the derivative at 2. Over here, if I'm trying to find the derivative of 8, I'm really looking for the derivative of 2, the inverse value. And that's actually what this equation said. The derivative of the inverse function is really the derivative of my original derivative, but with the inverse value, which is the x value. So if this is y in the real world, this is x in the real world. So why is this
So
important?
I have a question.
Yes.
Another question. So derivatives are the same as inverses?
No, but there's a relationship. It's just 1 over your original derivative. Okay. Now, why do we want to know this? Is because inverses are kind of trash because they take a lot of work to go through. If you remember this problem, I had to first solve the inverse and then take the derivative, and the derivative itself was ugly. But what if I told you it was just 1 over, well, sorry, if it was just 1 over 12 without going through any of these steps? So let's do the problem over again. If I tell you find the derivative of the inverse function, okay, and here's the inverse function, f inverse of x is equal to, let's do f of x is equal to the cube root of x. Let's say I give you the regular function and I ask you to find me the derivative of the inverse function. And I'm going to say at the number, find the derivative at the number f inverse of 8. Oh, no, not 8. We'll say 16. Okay. Well, we could solve for the inverse. You could say, well, the inverse is x squared. Right? You could do that. Isn't the inverse of this function x squared? But instead of doing all that work, the answer is this. It's 1 over, what is the inverse of this function? If 16 is my answer, okay, what answer led to 16? It's 256. So here's our x and y. Our x and y. If 16 is our, oops, my bad. If 16 is our x, our y is x squared. So this would be 256. So what's the derivative of this guy? Isn't the derivative just 1 over 2 squared of x? So the derivative is 1 over 2 squared of x. Whoops. 1 over 2 squared of x. Except the x is really the y. So the problem is 1 over 2 square root of 256. Square root of 256 takes us back to 16. 1 over 2 square root of, oops, 16. Whoops, I have another fraction. I keep saying whoops a lot today. 1 over 2 times 16, which is 32. Okay, let me do one more. Okay, d over dx, f inverse of x. Okay, this is essentially 1 over f prime of f inverse of x. Okay, that's what they want. That's what the rule says. So if f of x is equal to, let's do x cubed. So if I ask you the question, what is the derivative of f inverse at, let's do 8 again, because we just did it. This is 1 over, if I plug in 8, we should get 2. Because if I plug in 2, don't we get 8? Inverse operation is just flip the x's and the y's. So this is just 1 over f prime at 2. If you want to write the full rule, 1 over f prime of f inverse of 8. The inverse of 8 is just 2. And so this problem here, the derivative is 1 over 3x squared. Plug in 2, 1 over 12. Let me give you another problem. Here's 3, call that 5. And the slope, f prime of 3 is equal to 2. What is the derivative of the inverse at 5? This is all you need. I could draw you the inverse graph. I could point at 5. Inverse graph looks something like this maybe. 1, 2, 3, 4, 5. What's the slope going to be? It's 1 over f prime of, if you give me 5, you give me 3 instead. And what's the derivative at 3?
2.
1 over 2. If this is 2, this is 1 over 2. So the idea is whatever function you end up with, the inverse function is always just 1 over the original value. Now, let's look at today's work because it really just involves tables. So they give us everything we need to know here, but I'm gonna write a couple of things a little differently. So they asked us to find, okay, f has an inverse function f prime. If f of 5 is negative 2, let's try that as a point. Cool with a point, 5 comma negative 2, that's my x and y. And the derivative at 5 is negative 4. What is the derivative of the inverse function? This is what is the derivative of the inverse function at negative 2. Well, we said this is equal to 1 over f prime at, oops. Remember, if this is my original y value. So what's my x value? 5. And what's f prime of 5? 1 over negative 4. There's no work needed if they give you the original derivative. Let me do this again. Okay, let me just explain this one problem while you guys are copying it. I'm going to do the same problem over again. The derivative of the inverse function is equal to 1 over the derivative of the inverse here. So please look at this value here. What is the inverse of negative 2? Isn't the inverse of negative 2 bring you back to 5? Right? That's what inverses do. It undoes my problem. So if I say undo negative 2, that should bring you back to 5. So this is really 1 over f prime at 5. And what is the f prime of 5? 1 over negative 4. One divided by negative 4. I'm not sure it's going to work. Okay, let's do another one. Sorry, we're almost done. So write this out. We know the x and y. You don't have to, but I like seeing it this way. Okay, x's and y's. And in inverse world, this is x inverse and y inverse. Okay, that's not the right notation, but that's the idea. So they also told us the derivative of -7. Now, here is our problem. What is the derivative? The derivative of f inverse of 8, okay, is 1 over f prime. It's the derivative of my original function, but don't plug in 8, okay? Because what's the inverse of 8? -7. Answer is 1 over 9. Done. Because the inverse, so the derivative of the inverse function is exactly the same thing as the regular function, except it's 1 over that value. It's just 1 over that value. Okay, let's do this again. Let's go. It's annoying me. Uh-oh, don't tell my internet's dead. Oh no, we're good. Okay. Okay, again, the idea is x and y. This is x, this is y, okay? So inverse world, it's -3 gives me 5, okay? So f inverse of -3 is 5. That's the answer, because it brings you back. So what is the derivative of f inverse of -3? It's the same derivative as 1 over f of your original value. What's the original value? Takes you back to 5. 1 over 2. And why is that again? Is because when you look at the graphs of inverse functions, when we look at the x squared and the square root, all these values here are related to all these values here. 1 over 2, sorry, other way around. Two over 1 here is 1 over 2 here. Steeper, 4 over 1, flatter, 1 over 4. This is even a weird one. What's the slope here? 0, right? Is there a slope here? 0 over 1, 1 over 0, doesn't exist. Matches 100% completely. Only difference is just the flip version. But also be careful. If this is 4, wait, yeah, this is 4. This here is 2. This is 2. This is, what's it? Square root of 4 is 2. No, square root of, shoot, I think this is 1. That's 1. Whoops, I messed up there. Ignore this part. I can't think of it fast enough. Okay. But there's that relationship. I just couldn't come up with numbers fast enough. Okay. Let's do one last one, okay? To show you that this is actually a really easy relationship. Where's not letting me jump? Oh, internal error. No. So close. Uh-oh. I think it died. Anyways, okay. So, last point. If I give you a problem, 3, 2, and f prime of 3 is equal to 27, okay? Then I ask you, find the derivative of the inverse of 2. All you have to do is write 1 over the original derivative of the original, not add 2, but the inverse of 2. And the inverse of 2 is 3. And you're done. Okay. All right. Once we see this in the table form, it's the same exact thing, except they'll give you a lot of random numbers that don't mean anything. So please be able to to filter out all the fluff and then figure it out. All right. If you guys have any questions, you guys can feel free to email me and let me know. This starts off hopefully as super confusing and hopefully became an easy problem in the end, seeing out the relationships between the slopes of the functions and its inverse function.